In this video, we're going to look at a very big conjecture about the area accumulation functions. And this big conjecture was introduced in our last computer lab. To get started, I want to let f be a continuous function on an interval that contains the number a. And let me see. I'm going to put that a in a different color because I want it to be clear that that is a number. We define the area accumulation function, AF of x, to be equal to the integral from a to x of f of t dt for all x inside the interval. And I want to kind of remind you of what this looks like. So let's think about what that looks like. So this function looks like the following kind of thing. If I have a set of axes, and I draw a graph, and this is y is equal to f of x, and I pick a starting value that is going to be x is equal to a, or actually I really want this to be I want this to be a t-axis instead of an x-axis. So let me change this to f of t. So this axis is a t-axis, and this is the y-axis. If I pick a value x, so here's an x, this area here is equal to the integral between a and x of f of t dt, and that's just AF of x. And because we're integrating in the correct direction and our function is above the x-axis, in this particular case, a of x would actually be bigger than 0. On the other hand, if I picked an x out here and I look at the area that is accumulated as we go from a to x over this direction, that red area is indeed the area given by the integral from a to x of f of t dt, but because we are integrating in the backwards direction, the width is going to be negative, the height is going to be positive, and so this particular integral is actually going to be less than 0. Now, in the last computer lab, we looked at animations of this kind of a picture, and I want to look at one of those things in Mathematica, although we're not going to do the animation. So let's go over to the Mathematica window. So over here, I've got a function y is equal to f of t drawn in blue because this is the t-axis. And I have had Mathematica draw the area accumulation function in red. So this curve is y is equal to the area accumulation function. And what I want to notice is that there is a certain relationship between the area accumulation function and the function f, and it looks suspiciously like some of the things that we should remember about the relationship between a graph of a function and the graph of its derivative. So let me start drawing some lines on this. When y is equal to f of x crosses the x-axis, it turns out that the accumulation function seems to be at an extreme point. So if you look at these lines that I've drawn, you can see that the red curve seems to be at an extreme point when the blue curve is crossing the t-axis. Now there's something else that I also kind of want to point out. This chunk here, f is less than 0, and the area accumulation function is going down. And here f is bigger than 0, and the accumulation function is going up. Here f is negative and the accumulation function is going down. On this whole chunk, f is positive and the area accumulation function is increasing. Over here, f is negative and the area accumulation function is going down again. And finally, f is positive and the area accumulation function is going up. And all of these things are very definitely reminiscent of the property of a function and its derivative. A function goes up when its derivative is positive. A function goes down when its derivative is negative. A function has an extreme point when its derivative is 0. All of this stuff here is saying that it might be the case that the derivative of the area accumulation function is equal to f, because they have the right relation. When f is positive, A is going up. When f is negative, A is going down. When f is 0, A has an extreme point. Well, there's another thing that we also know about the graph of a function and its derivative graph. And so I want to kind of eliminate a lot of the drawing that I've done so far, because I want to look at another set of points on the f graph and see what's happening on the a of f graph. So let me get these things all cleared up. And let me label the graphs again. This is y is equal to af of x, and this is y is equal to f of x. And now let's look at some additional lines. Well, let's see, I've got some straight lines. So let me finish getting rid of these lines, because I don't want them anymore. I'm going to look at places where the f graph has an extreme point. And I'm going to connect them to places where, to the red graph. So all of these line segments have, the f graph has an extreme point, and I'm wanting to see what's going on the red graph. So let's look at the red graph. Here's the extreme point on f, and up here it looks like we're pretty close to an inflection point, because if I'm thinking about this, this is concave, this appears to be concave down, and this is clearly concave up. Here we're getting another inflection point. The red graph is going from concave up to concave down. We get another inflection point here, going from concave down to concave up. This is another inflection point, and this is another inflection point. In other words, we see that AF has inflection points when F has extreme points, and that is another thing that says it might be the case that the derivative of the area accumulation function just might be the f function. And that's the major conjecture that comes out of looking at all of these graphs that Mathematica has drawn from us in the previous lab. So I want to state that conjecture carefully and formally back in my other notebook. So let's come back over here and clear some stray stuff. So I want to actually write this as a conjecture. If f is a continuous function on an interval containing the number a, and we defined the area accumulation function to be the definite integral from a to x of f of t dt, then the derivative of that area accumulation function just happens to be f of x. We'll look at the proof of this particular conjecture in the next video.